Hello everybody, this is Nageswara, Assistant Professor of Physics, Government Degree College, Chintalapudi. In this presentation, I want to introduce interference. How many types of interference? How can we get bright and dark fringes by the interference pattern? So before discussing about the interference, you want to remember principle of superposition. According to principles of superposition, if the resultant displacement of a particle of the medium acted by two or more waves simultaneously is the algebraic sum of the displacement of the particle due to individual waves in the absence of the others. For example, if this is a point in which a wave is introduced or incident on the particle, the displacement is moved from here to here. It may be taken as y1. If another wave is in the same direction is incident on the particle will move from one place to another place. If this displacement is y2, then the resultant displacement of the particle is y1 plus y2. This is called principle of superposition of waves. So, if y1 and y2 are two displacements of the particle, then the resultant displacement y can be expressed as y is equal to y1 plus y2 or y1 is equal to y1 minus y2. Why it is minus is if particle is moved in opposite direction due to the two waves, then the resultant displacement is the difference of the two displacement. So it is taken as algebraic sum of the displacement. So the principle of superposition of states that the resultant displacement of a particle of the medium acted upon by two or more waves simultaneously is the algebraic sum of the displacement of the same particle due to individual waves in the absence of others. So this is one wave, wave 1, this is another wave. Superimpose on each other, then the amplitude or increases like this. In this case, the displacement y is equal to y1 plus y2. In this case, the two waves are whose this is crest and trough are in the same place. So that the resultant displacement y is equal to 0. So this represents the principle of superposition of waves. So what is interference? If two waves, that is two coherent waves, superimpose each other, the resultant amplitude or intensity in the region of superposition is different than the amplitude or intensity of individual waves. Due to the superposition of these two waves, there is bright fringes or dark fringes are observed. This phenomena is called interference. It means the modification in the distribution of intensity in the region of superposition is called interference. So there is bright fringes and dark fringes occurs in this superposition of two waves can be explained by constructive interference and destructive interference. What is constructive interference? When the two waves superimpose each other, then the resultant amplitude is the sum of amplitudes due to the two waves, then the interference is known as constructive interference. So that the resultant amplitude or displacement y is equal to y1 plus y2. What is destructive interference? When two coherent sources superimpose each other, the resultant amplitude is the difference of the two amplitudes. Such interference is known as destructive interference. So when the two waves superimpose each other, the resultant amplitude is equal to the difference of the amplitudes, then the interference is known as destructive interference. So that the displacement can be written as y is equal to y1 minus y2. So same diagram we can see here. So in the first case is constructive interference in the amplitude is increases. This is the second case, this is destructive interference, the amplitude is nearly 0. And what are coherent sources? So to observe the interference pattern, coherent sources are compulsory. What is this coherent sources? Coherent sources is nothing but the two waves having constant phase difference. So this can be explained as follows, where S1 and S2 are two sources of same wavelength and AB is the screen and the dots and the dashes are given in this figure at different places alternatively. The dots represents the points for which the distance from S1 and S2 differ by n lambda. For example, the center dot is the phase path difference is 0 because S12 and S2 this place is equal, so the path difference is 0. From this S12 first point and S22 first point, it is the path difference is lambda, and S12 second point, S22 second point is path difference is 2 lambda, etc. So that the path difference is equal to n lambda, where n is the integer. In case of dashes, the path difference is 2n plus 1 into lambda by 2 or n plus half into lambda by 2 between two waves which is passing from S1 to S1 and S2. And now we can see the following cases. So there is S1 and S2 there. The waves will move from S1 and S1 to the center point. We know in this case the path difference is 0, so that phase difference is also 0. It is nothing but these two S1 and S2 are in same phase. If S1 and S2 are same phase, we can see the dot is bright fringe and all the dots are, we can see bright fringes, and all dashes will observe as dark fringes. So in case all the dots on the screen will be bright while the dashes will be dark at all times. So we get a stationary interference pattern on the screen in this case. So from S1 and S2 the waves will move dash, and in the same way the waves is passing from S1 and S2 reach different places as shown in the figure, and at last the ray is moving from S1 to S2 and reach the dash. And the second case, when the two waves starting from S1 and S2 having phase difference by pi radian, that is path difference by lambda by 2, in which case all the dots are shows dark fringes and all the dashes shows bright fringes. So the waves starting from S1 and S2 differ in phase by pi radian. In this case, all the dots on the screen will be dark while the dashes will be bright at all times. So we get a stationary interference pattern on the screen. It is nothing but if the phase difference is 0 or if the phase difference is pi, we can get the stationary interference. So if the phase difference between S1 and S2 is differ by constant phase, that is nothing but 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, 5 pi, 6 pi, and so on. Also we can get the bright and dark fringes. Maybe the intensity changed from point to point. So we can see once again there is a light rays which is passing from S1 and S2 to reach the points and the dashes on the screen, and they formed dark fringes and bright fringes alternatively on the screen. If the phase difference between S1 and S2 is changing randomly with the time, at this case, the interference pattern also changes randomly with the time, so we cannot observe the interference pattern by human eye. So that the intensity is ever uniform everywhere on the screen. It is nothing but if the phase difference between S1 and S2 is differed by phase changes with random with time, the interference pattern cannot observe. So the two sources which maintain zero or constant phase difference between themselves are known as coherent sources. This phenomena is called coherence. So, to observe the interference pattern, the sources must be coherent. It is nothing but the phase difference must be zero or constant. So, to observe the interference pattern by using a light, following conditions must be fulfilled. There is some conditions are required to obtain a permanent stationary interference pattern. The conditions are classified in the following three parts. The first one is condition for sustained interference. Second one is conditions for observation of the fringes and conditions for good contrast between maxima and minima. It is nothing but some conditions to be fulfilled to observe the sustained interference. What are they? So these are the conditions for sustained interference pattern. The two sources should be coherent. It is nothing but they should vibrate in the same phase or constant in phase difference. Then only we can see the sustained interference. So we know the resultant intensity of two waves is I is equal to A1 square plus A2 square plus 2A1 A2 cos delta, where A1 and A2 are amplitudes of two waves individually. The second point to obtain the sustained interference is two sources must emit continuous waves of the same wavelength and time period. It is nothing but two sources as shown in the figure S1 and S2 must have same amplitude and same time period. It is nothing but the frequency of the two waves must be equal. These are the two conditions to observe the sustained interference. So what are the conditions for observation of the fringes, interference fringes? We know the fringe width beta is equal to lambda d by 2 small d, where beta is the fringe width, the distance between two consecutive bright fringes, are also called two consecutive dark fringes. That is called fringe width, where lambda is the wavelength of light, capital D is the distance between slit and screen, 2D is the distance between two slits, that is two coherent sources. So by using this principle, we can say the conditions for observation of interference fringes. The first one is the separation between two sources 2D should be very small. As shown in this figure, if the small 2D is very small, beta is very high. So to observe the interference fringes, fringe width must be more. So that if 2D is very small, we can see the interference fringes easily. And second condition is the distance capital D between the two sources and the screen should be large. It is nothing but as shown in this figure, if capital D is more, the fringe width is also more, so we can easily see the observe the interference fringes. And third point is the background should be dark. If the background is dark, we can see easily if the intensity of the bright and dark if bright fringes are even though less. These are the conditions to observe the interference fringes. So, what are the conditions to observe the interference fringes with good contrast? Good contrast is nothing but the intensity is more for the bright fringes. Intensity is very less for the dark fringes. We know the resultant intensity I is equal to A1 square plus A2 square plus 2A1 A2 cos delta, where A1 and A2 are amplitudes of two waves. Delta is the phase difference. We know if delta is equal to 0 or maybe pi or 2 pi, then the intensity I is equal to A1 plus or minus A2 whole square. So the first condition for good contrast is the amplitudes of the two waves must be equal. That is, if A1 is equal to A2, the intensity is maximum for constructive interference, that is I is equal to A plus A whole square, that is 2A 4A square. So 4A square is the maximum intensity of the bright fringe. If for the destructive interference A1 minus A2, that is 0, so the resultant intensity is 0, so we can see bright and dark fringes accurately. The second condition to observe good contrast is the sources must be narrow. That is, they must be extremely small. It is nothing but the slit is very narrow. Then also we can see the good contrast. Our third case is the source should be monochromatic. It is nothing but single wavelength or a single color. If the source is single color, then the interference fringes can see the same color. If it is white light or multicolored, the interference fringes are very little. These are the special conditions to observe the interference accurately. And also, two more concepts are required to observe the interference, that is, spatial coherence and temporal coherence. The phase condition at a point on the screen are determined by the following two factors. One is phase condition of two sources, and second one is phase condition developed their journey towards the superposition of point. In order to link up the formation of interference due to these factors, we now introduce the two types of coherence. One is spatial coherence and second one is temporal coherence. So we will discuss it is spatial coherence and temporal coherence one by one. What is spatial coherence? In this diagram, we have source S, that is point source. There is S1 and S2 are two slits. If the light is incident on two slits, these two rays are came from the two slits having equal amplitude and equal frequency and same wavelength. And this is AB is the screen. So the two sources S1 and S2 are derived from the same source with the help of a pinhole S. We consider the following situations. The first point is keeping the opening of the source pinhole S is fixed and the slits S1 and S2 be either widened. It is nothing but the 2D is increases. We know if 2D increases, we know according to the formula beta is equal to lambda into capital D by 2D. If 2D increases, beta decreases. It is nothing but two fringes are very near to each other. Two bright fringes are very near. So we cannot observe the free interference pattern. So keeping the opening of the pinhole S is fixed. Let the pinhole slits S1 and S2 either widen or their separation, that is 2 dB increased. In such case, it is observed that the fringes appear to lose distinctiveness or contrast. The second point, if keeping the two slits S1 and S2 in their proper opening, it is nothing but 2D kept constant. Let the opening of S be widened. In this case also, the fringes appear to lose sharpness or contrast. It is nothing but we cannot see the interference pattern accurately. In the above two cases, we say that phase condition of two sources is disturbed. That is, spatial coherence is on the wave. Further, if the two sources are independent sources, it is nothing but it is not came from the same source, single source, is if it is two sources are individual. Even though those wavelengths are equal, the phase changes randomly with time. So in this case also we cannot see the interference, it loses spatial coherence. So and hence no interference is possible. Therefore, if the phase difference for any two fixed points in a plane normal to the wave propagation does not vary with time, then the wave is said to exhibit spatial coherence. So, in this case, spatial coherence, there is no obstruct in the passage of two light rays. If one of the ray is obstructed by any transparent material just like mica, then what happens? That is explained by using temporal coherence. So, what is temporal coherence? The consider the situation in which the path of the one beam is extended. This can be done by introducing a transparent sheet like mica or plastic paper in one part of the taking the point of observation at a large distance. It is observed that if the difference exceeds the coherence length by LC is equal to C into LC, then the interference fringes lose sharpness and contrast. Now we say that the beam lack in temporal coherence. So in this case, this is S1, this is S2, this is the screen. We know these rays will move along this direction. If one of the rays is obstructed by any transparent material or maybe like mica, there is disturbance occurs in the path of the beam. When this case it loses its coherence, that is also called lack in temporal coherence. So for a particular value of plate thickness or a particular value of path difference, the temporal coherence is completely lost. As a result, the fringe pattern disappears. To obtain a permanent interference pattern with sufficient contrast, both spatial coherence and temporal coherence are necessary. Thank you.